Hello, and in part 2 of these talks about op-amps, introducing the concept of negative feedback. And this is the technique which turns operational amplifiers into incredibly useful multi-purpose amplifier blocks. Negative feedback involves taking some sample of the output of an amplifier and feeding it back into the negative input of that amplifier. So it acts, in effect, to reduce the gain, this gain that we're assuming is infinite. The circuit here has a fairly extreme form of negative feedback. I've connected its inverting input, the negative input, directly to the output. So the inverting input of this amplifier is at the same voltage as its output. And that gives me an amplifier here which has one input voltage. I've called it Vin, connected directly to the non-inverting input of this op-amp. Then if I go through the maths of what happens, I'll find that Vout equals the open loop gain A, which we're assuming to be very large, times the non-inverting input minus the inverting input of this amplifier. The inverting input, however, is connected directly to Vout, and the non-inverting input is connected to the input of my amplifier Vin. So that produces this expression, A times Vin minus Vout. If I do a bit of algebra on this, first multiply out this bracket, A Vin minus A Vout, and collect terms in Vout on the left-hand side, I will get this. Divide through by 1 plus A, and I'll get that Vout is equal to A over 1 plus A times Vin. Now, we're assuming that A is a very large number, effectively infinite. So if A is very, very large, then A over 1 plus A will be approximately equal to 1. The 1 becomes negligible with respect to the A. And that gives us that Vout is proximally equal to Vin. And as A tends to infinity, that approximately equal sign becomes an actual equal sign. So I have here an amplifier that will give me an output which is equal to its input. It's not saturating anymore. We can check this works on the simulator. This is the circuit that we saw before, with the output of the op-amp saturating all the time. But if I disconnect the inverting input to the op-amp from ground, and connect it instead around to the output, then you'll see the output of the op-amp is equal to its input in all cases. It's something that we call a unity gain buffer, or a voltage follower. Just the output voltage equals the input voltage. This form of negative feedback is quite stable, in the sense that if any slight disturbance happens to your circuit, the action of the feedback will be to bring the circuit back to its stable operating point. And you can see that by looking at this equation again. If anything happened such that Vout became slightly too big, a bit of noise or something in the circuitry, so Vout became slightly bigger than Vin, then if Vout increases, then V plus minus Vout will decrease, which will mean Vout will head back down again. It's being pulled back to its stable equilibrium point by the action of the negative feedback. Similarly, if Vout ever went slightly below Vin, then V plus minus Vout would increase, and that would push Vout back up again. So the action of this negative feedback is to maintain that stable equilibrium point. At this point, you might be wondering what the point is of an amplifier if all it does is give you an output voltage which is equal to its input voltage. Why bother having an amplifier there at all if it doesn't change the voltage? Well, consider this. What would the voltmeter read in this circuit? And you've probably identified this by now. It's everyone's favourite circuit. It's a potential divider. It's a very simple potential divider because the two resistors are equal. So the output would just be half of the input voltage, 1 volt. The voltmeter would read half a volt, 500 millivolts. Right. But what about this one? I've inserted here a unity gain buffer, an op-amp which ensures that its output voltage is equal to its input voltage all the time. Now what would the voltmeter read? And the answer is 1 volt. Because, remember the properties of an ideal op-amp. No current flows in to an ideal op-amp. Therefore, there is no current flowing through this 1K resistor, which means there is no voltage dropped across this 1K resistor, so the non-inverting input here will just be at 1 volt. This is a unity gain buffer, so its output voltage will be at 1 volt as well. An ideal op-amp has an output resistance of 0, so I could replace this op-amp by a Thevenin equivalent circuit, which looked like this. 1 volt, 0 ohms, output of my op-amp there, and that is what is connected to the voltmeter. There is also a 1K resistor down here, but all that does is it drags 1 milliamp of current out of the op-amp. It doesn't change the voltage at the output of the op-amp at all. The voltmeter would read 1 volt. This has solved the problem of circuit loading that we discussed in an earlier video. I could change the value of this resistor here, this 1K resistor. I could make it anything I liked, and the voltmeter would still read 1 volt. Similarly, this 1K resistor could take any value I wanted, and it wouldn't change the fact that the voltmeter here would read the value of the voltage source there. The output resistance of this circuit or the input resistance of any circuit here don't make any difference. The voltmeter would read the voltage source voltage from here. That is the real power of a unity gain buffer like this. In the next video, we'll have a look at positive feedback and what happens if you take a sample of the output voltage and put it back into the non-inverting input.